Hi. In this brief 10-minute video, I'd like to describe some of the characteristics that make a good buffer. And in particular, we're going to look at how the composition of the buffer can be used to determine the pH of the solution. We'll do this in two ways. We'll look at it more of a brute force approach, where we use the rigorous rules of ice tables and using KAs, and then we'll look at a simpler, perhaps more elegant approach using the Henderson Hasselbalch equation. So as a concept that I'd like to use to frame this discussion, my general question is, what is the pH of a buffer that consists of a solution that is 0.1 molar in acetic acid and 0.2 molar sodium acetate? And so a very simple way of thinking about this is to say we have a liter of solution, we have 0.1 moles of acetic acid, and we've added 0.2 moles of sodium acetate to this solution. So this is a classical recipe for a buffer. A buffer is, generally speaking, a mixture of an acid, and not just any old acid, but a weak acid, and a conjugate base. And again, not just any old conjugate base, but the conjugate base of the acid that we're talking about. So for my weak acid, I'm going to use acetic acid, which has the Lewis structure like this. And for the conjugate base, I'm going to use acetate ion, which has this structure. Of course, acetate ion has a resonance structure that we could draw this way. And one of the characteristics of carboxylic acids is that they're more acidic than alcohols because we can delocalize the minus charge through the carbonyl oxygen. So we have these two players, the acid, the weak acid, and its conjugate base, and these two comprise a buffer. Here are some examples of some other good buffers. HCN is a weak acid, and its conjugate base is cyanide ion. HF is a weak acid, and its conjugate base is fluoride ion. These would all be good buffers because they consist of a weak acid and its conjugate base. For diprotics, we could think of some others. H2CO3, HCO3 minus, that is carbonic acid and bicarbonate ion, or bicarbonate, HCO3 minus, and CO3 2 minus would be a good buffer because, again, it consists of the acid form, bicarbonate, and its conjugate base, or carbonate ion. But what are some poor choices for buffers? If these are all good, if HCN and cyanide is good, and carbonic acid and bicarbonate is good, and bicarbonate and carbonate are all good, here are some poor choices for buffers: HCl and chloride ion. So the reason HCl and chloride ion, well, it's true that chloride ion is the conjugate base of hydrochloric acid. The problem is that HCl is not weak. It's actually a very strong acid. Another poor choice for buffer would be something like, so that's a bad choice. Another bad choice would be HCN and fluoride ion. And the reason why HCN and fluoride ion would be a poor acid-base combination is because fluoride is not the conjugate base of HCN, rather fluoride ion is the conjugate base of hydrofluoric acid. So the critical point is that a buffer consists of a weak acid and its conjugate. In this example, we'll talk about acetic acid and its conjugate base, acetate ion. So to continue our discussion of acetic acid and acetate ion, the acid-base reaction that relates these two species is very simple. It's acetic acid, or HOAC, I'm going to use the abbreviated form, plus water is in equilibrium with OAC minus plus H3O plus. This is a typical acid-base reaction. In this example, acetic acid is the acid, water is the base, acetate ion is the conjugate base of the acid, acetic acid, and hydronium ion is the conjugate acid of the base, water. So now in this example, the concentration of acetic acid is 0.1 molar. The concentration of acetate ion is 0.2 molar. And now for other species, the concentration of water is kind of unimportant because we don't include the concentration of water in equilibrium expressions. And the concentration of H3O plus typically is small, around 10 to the minus 7th, but for our purposes we could say that this is approximately 0. And what this tells us is that if this is the initial concentration of all the species, then we can say right off the bat that Q, which has the form of the acetate ion concentration times the hydronium ion concentration divided by the acetic acid concentration, is actually less than K. So we know that as the system approaches equilibrium, the reaction, we're going to react acetic acid with water to form a little bit more acetate and a little bit more hydronium ion. And this leads to a change in the concentration that we can reflect as a change in concentration. We're going to say that the acetic acid concentration is going to decrease by some quantity. We'll call it X. The acetate ion concentration is going to increase by X, and the hydronium ion concentration is going to increase by X as well. And the fact that the acetic acid concentration decreases by the same amount that the acetate ion and the hydronium increases is logical because, first off, there's 1-to-1 to 1 stoichiometry in our balanced equation. So as the acetic acid concentration decreases, we should see an equal reaction, but in the other direction, for the formation of acetate ion and hydronium. So we see the acetic acid decreases, the acetate ion and the hydronium increase, and then at equilibrium, we have 0.1 minus X and 0.2 plus X and X. And so for this reaction, we have Ka is acetate ion times the hydronium ion concentration divided by the acetic acid concentration, which in this example is 0.2 plus X times X divided by 0.1. And so Ka equals 0.2 plus X times X divided by 0.1 minus X. Now, because acetic acid is a weak acid, the truth is that it won't dissociate very much. And so relative to 0.1, X is small. In fact, relative to 0.2, X is also small. So this expression can be simplified to be 0.2 times X divided by 0.1. And so really what we're saying is that X is much, much less than 0.1. In other words, 0.2 plus X is around the same as 0.2. 0.1 minus X is around the same as 0.1. And so we can say that Ka now equals 2X, which for acetic acid is 1.8 times 10 to the minus fifth. In other words, X equals 0.9 times 10 to the minus fifth, and that equals the H3O plus concentration. And now, because the H3O plus concentration is 0.9 times 10 to the minus fifth, we can say that pH equals minus log H3O plus, which equals about 5.0. I think we could say that this would be considered a brute force approach to this problem. We have the acid, acetic acid, we have the base, acetate ion, we have an acid-base reaction that relates the two. Acetic acid plus water makes acetate plus hydronium ion, and we used an ice table to figure out the initial changing and equilibrium concentrations of all the species to determine the equilibrium concentration of H3O+. A simpler and perhaps more elegant approach is to use what's called the Henderson Hasselbalch equation. And so to introduce the Henderson Hasselbalch equation, we need only start with an expression for Ka. Ka, in this example, is acetate ion concentration times hydronium ion concentration divided by the acetic acid concentration. Now if we take the minus log of both sides, that's straightforward enough, but what I'm going to do is I'm going to partition the right-hand side into a part that contains the acetate ion and the acetic acid and the hydronium ion as separate entities. And so we can say that this is minus log Ka equals minus log OAC minus divided by HOAC minus log H3O plus. And so if you look at this expression, you can see that this is really just pKa, or minus log Ka. P is just minus log of anything. You can literally P anything. This equals minus log acetate ion concentration divided by acetic acid concentration. And now minus log H3O plus, well, that's really just plus pH. And so to rearrange this, we have pH equals pKa plus log OAC minus divided by HOAC. And this is known as the Henderson Hasselbalch equation. It has no relation to David Hasselhoff or Knight Rider or Baywatch or any of those things, but it's extremely valuable in understanding and predicting the pH of a buffer solution once we know the pKa. And now in this example, acetic acid has a Ka of 1.8 times 10 to the minus fifth. That corresponds to a pKa of about 4.74. And so pH equals 4.74 or 4.7 plus log of the concentration of acetate ion, or 0.2, divided by the concentration of acetic acid, or 0.1, which works out to be exactly 5.0. And so the point of this is simply that the Henderson-Hasselbalch equation is a short way of predicting the pH of a solution of an acid and its conjugate base. It has great value because the percent association is relatively small compared with the concentration of the acid in the conjugate base form. And it's a really simple way of looking at the ratio of the acid in the conjugate base form in order to find the pH of a solution. Thank you very much.